Welcome to the course on switching and automata theory. This is our first lecture, and let us initially see that what we are going to discuss. Okay, the course is on switching and finite automata theory. Let's see that what we would like to discuss here. Let's say a switching circuit. Let's first have a black box. Okay, this particular black box, say, has several inputs to it. It has, these are inputs to the switching circuit. I call it a switching circuit. What exactly it contains, etc., we'll see. It can have outputs. It can have, say, a single output, or it can have several outputs also. Okay, let's see the number of inputs: I1, I2, I3 to say IP, the P number of inputs. Okay, and let the outputs be O1, O2, OQ, so Q number of outputs, right? Each of these inputs or each of these outputs, they can take either of two values. Okay, either it is 0 or it is 1. Okay, that means we call it a binary input or binary output, right? Now the situation is, and this is called combinational circuit. Okay, this is a combinational circuit. Now the purpose of this class will be that, given a particular specifications, that means that these are the inputs, okay, these are the outputs. The inputs can have these combinations for which I want a particular output to be 1 or 0, given this kind of specifications, right? One purpose of this class is to find out what circuit it will be. Okay, right. Specifically, I mean, say for example, if we have 3 input circuit, okay, and 1 output, that means, for example, if the situation is like this, that we have only 3 inputs and we have 1 output, right? Say for example, x1 is an input, x2 is an input, x3 is an input, okay, and say z1 is an output, right? Then, for example, the specification may be that the combinations of 0 or 1 for each of x1, x2, and x3, okay, when the output z1 will be 0 or when the output z1 will be 1. For example, this we can enumerate as this. So, for example, say x1, x2, x3, right? Say input different combinations can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7. These are the 8 possible combinations of x1, x2, and x3, the inputs that we can have. We can say that we want the output z to be, say, 0 over here, 1 over here, 1 over here, 0 over here, 1 over here, 0 over here, 1 and 1 over here, right? Say this is the situation, right? And we would like to determine what will be the circuits, okay, so that this input output characteristic is obtained, right? Now, this is one aspect of it. Another aspect is that, for example, this circuit is given. Once more, let's see. This circuit is given, right? And we would like to know this circuit corresponds to what input-output behavior, right? The previous one, that when we are giving the specifications, we are going to have the circuit, design the circuit, is called the synthesis. And another situation is that given the circuit, right, we want to know what input-output behavior it is showing. Okay, it's the analysis. Therefore, our purpose in this course will be that both analysis as well as synthesis. That means given specifications, we'd like to come to this realization, or given a realization, we'd like to come to how that, what exactly is the realizations? That means what's the behavior of the circuit, right? Now, we call this a combinational circuit. By that I mean that output at any instant of time, that if we take an instant of time t, the output at any instant of time, okay, will be essentially dependent upon the inputs exactly at that instant of time, right? At any instant of time, the output is dependent upon the inputs at that instant of time, right? It is called a combinational circuit to distinguish it, as you can very easily feel now, that from another circuit which we call a sequential circuit. In the case of a sequential circuit, what happens is this: it has also several inputs. It may have also one or several outputs, right? Of course, the difference is the output at any instant of time, okay, may not be dependent upon the input at that instant of time. It depends in general, okay, the history of the input. That means the inputs that were applied to it in the past as well, okay. That is why it is called a sequential circuit, right? In such cases, that we are interested in finding out that what is the sequence of outputs that is produced, okay, in response to the sequence of inputs, right? Since it is now dependent upon the past inputs as well, okay, right? Therefore, we do not talk about a particular input corresponding to an output. We talk about sequences of outputs in response to sequences of inputs. Right. Now, to have such a behavior, therefore, a sequential circuit would have memory elements. It has to remember what was the previous history. Okay, it has to keep that in mind. Therefore, it has we call it that it has a memory elements. The general, I should say, the nature of the circuit will be like this. I'm showing you by means of a diagram. That once more, that let's see. This is a box that we have, right? Say, it can have, say, some inputs, right? We call this as primary inputs, right? It has some outputs, okay? Apart from that, what it has is essentially that Okay. Some other outputs, okay, which is fed to, we call them to be memory elements, right? Therefore, here what happens is this, that we have some primary inputs, you have correspondingly some outputs, okay? Apart from that, you have certain, so to say, secondary inputs, right? These are coming from the outputs of some memory elements. The memory elements are in fact the flip-flops, okay? Different kind of flip-flops that we have, right? That say JK, ESA, D, that different kind of flip-flops that we keep. Each can contain one bit of information over here, right? These are fed, okay, or excited by means of some secondary outputs, okay, which are fed as an excitation to this. The state of these flip-flops changes and the output of these flip-flops is fed back to this circuit. And this circuit is a combinational logic once more, okay? Therefore, this in fact is a sequential circuit. Now, you can distinguish it very, I should say that distinctly from a combinational circuit, that in a combinational circuit, we have that inputs and outputs, there is no feedback associated with it, no memory elements associated with it. Here is a combinational logic that we have, a combinational circuit that we have, okay? And in the case of a sequential circuit, we had certain memory elements, right? This is a combinational logic once more, but this feedback is made available over to there, and this makes it dependent upon the previous input, because the state of this, okay, flip-flops will be dependent upon what input was applied previously, and since this comes as a secondary input once more to this combinational circuit, the outputs being dependent upon the primary inputs as well as the secondary inputs will be dependent upon what input was applied to it in the past, right? Once more, our endeavor will be here to analyze as well as synthesize a sequential logic circuit as well, okay? By that I mean that given a specification that this I want, right? That say, for example, that the output, a single output, should become turned out to be 1 if any time the input, say a single input, okay, have 3 consecutive zeros, right? That means whenever I'm going on giving a series of inputs, a sequence of inputs to the circuit, let it be a single input, single output circuit, I'm going on giving a sequence of inputs, right? I want that output will be 1 whenever I find that 3 consecutive zeros have appeared in the input, right? Immediately the output will be 1. Otherwise, the output remains 0. Is it okay? That's essentially a sequential circuit that cannot be done by means of combinational logic alone, right? And that way, that is specification given, our purpose will be come to a circuit realization of it, okay, right? A realization of it, and similarly, given a sequential circuit, right? Okay, given a sequential circuit, our purpose, our endeavor will be, right, to analyze it so that we know that for any input combinations or any input sequence that I give to it, okay, what will be the output sequence that should be able to find out, right? Now, to do all these things, right, to maneuver, manipulate, okay, so that and to do analysis and synthesis of the switching functions as well as the sequential circuits, right? What we need is an algebra, okay? The basics of that manipulations, etc., will be dependent upon, will be based upon that algebra, which we probably you know already. It's called a name. You have heard the name of it. It's called a Boolean algebra, right? Therefore, our purpose of this first lecture will be to introduce Boolean algebra and to show from there that what is a switching algebra. That means a special case of a Boolean algebra, right? Therefore, let's start with the Boolean algebra. Yes.
In the last diagram you showed, sir, when at any instant we give an input, some of the output is fed back to the input. Is that delivered for the next instant?
That's right. We'll talk about it. Basically, it's called synchronous sequential circuit. There are asynchronous sequential circuit, right? Therefore, exactly how and what instant of time it gets feedback, okay, that depends upon whether the circuit is sequential or asynchronous. So, example, in the case of a sequential circuit, what happens that we have a clock, right? Therefore, what output comes out over here, right, that gets effective, right, at the next instant of time. This instant of time, the state changes over to here, and the change state becomes effective at the next instant of time. Okay, that's, I should say, that synchronous or clock sequential circuit. In the case of an asynchronous sequential circuit, right, this comes over to here, right, and it automatically it gets fed back, right, and as it gets fed back into the circuit changes and ultimately comes to a stable state. Okay, and we'll talk about that stable state in that case. Therefore, those details we'll talk about when we come to it. Right? Yes.
So what is automata?
Now, naturally, that has been the course name is switching and finite automata. Now, the mathematical model of a sequential circuit is called an automata. Okay. Therefore, we'll have a mathematical model for it. We'll call it as a model for it. We call that as an automata. And we call it a finite automata because the number of flip-flops is finite over here, and therefore the number of states are finite. Okay, and therefore it's called a finite automata. Okay. For analysis and synthesis of combinational circuits, right, and the combinational circuits that is used in sequential circuits as well, okay, we need the help of an algebra we call the Boolean algebra. For example, that given the switching functions, to change the switching functions, okay, or to come to a switching function, right, we need this algebra, and therefore let us introduce this algebra first. Okay, this algebra was introduced by George Boole in 1854, right, and essentially it consists of a set B consisting of several elements, say A, B, C, right, two binary operators plus and dot, this being the binary operators, and one unary operator, right, dash, and this, okay, satisfying the following, and the following axioms are there. Okay, satisfying the following axioms. The axioms are, let's repeat once more. We say that we have a set B consisting of several elements, A, B, C, etc. We have two binary operators. One we call this plus, another is dot, right? One dash being an unary operator, right? By binary operator, I mean two operands are there. Unary operator means that there is only one operand there, right? These are satisfying the following axioms. The following axioms hold. Okay, let us see what are the axioms, all right? One is that, say, axiom 1, that the set B should consist of at least two elements. Set B consists of at least two elements, right? Axiom 2 is closure. That for every AB contained in B, right, A plus B is also is in B, A dot B is also in B, right? Acha. Now, commutation laws. That for every, this says that for every AB contained in B, A plus B is equal to B plus A dot B is equal to B dot A, right? Let's come to the axiom 4 is associative laws, right? Once more, for every A, B, C contained in B, this is valid. That means A plus B plus C is equal to A plus B plus C equal to A plus B plus C. Okay. Similarly, A dot B dot C is equal to A dot B dot C Acha. Next comes, say, my A5, right, is distributive laws. This says that A plus, right, rather let me write it this way, is A plus B dot C equal to A plus B dot A plus C, and A dot B plus C A dot B plus A dot C, right? This is a distributive law. That means plus is distributed over dot, and here the dot is distributed over plus, all right? Now, A6 are the identity elements, right? We introduce identity elements now. That there exists an identity element, okay? We denote this 0 for plus, right? Another identity element 1 for dot, such that A plus 0 is equal to A dot 1 is equal to A, where A, 0 and 1 are all contained in B, right? And let I repeat once more that the identity elements, there are two identity elements, one is 0 for plus and there is 1 for dot, such that this is true. That means A plus 0 is A dot 1 is equal to A, right? A, 0 and 1 are all elements of B. Okay. This is, and now let's come to A7, that is complement. It says that for each A contained in B, there exists another element A dashed contained in B such that A plus A dashed is equal to 1, A dot A dashed is equal to 0, right? A plus A dashed is 1, that means identity element for dot, and A dot A dashed equal to 0, which is identity element for plus, right? Now, these are the basic postulates, right, on which we will now develop certain theorems, right? These theorems will be used as the rules. I mean, the postulates of the theorems, they will be used as the rules of our Boolean algebra. Now, the first theorem that we say is this, say theorem 1. Up to this, it's all right, what I have said? Yes.
How A plus B dot C is A plus B dot C? Because the second one is obvious, but this is just confusing.
Once more.
A plus B dot C is equal to A plus B dot A plus C.
A plus B
Dot A plus C. So A5.
No, A5. A plus B dot C is A plus B dot A plus C. It's basically a distributive law. Okay, it's a postulate we assume to be true, right? Right. I mean, what is the? We have not. This is essentially, what should I say? That we have kept it in a very abstract way. We have not given any interpretation to it. We'll come to the interpretation to it. Right. Now the situation is, as I told you from the very beginning. Let's say come over to here. Okay. That we are talking about the. Just to repeat once more, they are talking about Boolean algebra. The entire thing is now being placed, so to say, in a very abstract way. We said that we have a set B. Just to repeat, we have said that we have a set B. It consists of several elements. Okay, it's a non-empty set. We have taken two binary operators. One is plus, another is dot. We have taken one unary operator. Is okay, right? We have not said what is this binary operators, what is this set exactly, etc. We have just said that there is a set, right? We have not said that what binary operators are these, what exact operators are these. Therefore, we have taken it to be quite, I should say, an abstraction. We have not given any interpretation to it. We'll come, when we give examples, we'll come to an interpretation of it. That what do I mean by plus, what do I mean by dot, what is exactly my set, etc. Right? Now, Boolean algebra consists of these three and some certain axioms. Okay, axioms we take it to be that it's true, okay, without being, I should say that it should be, it's supposed to be true that without any supporting proof of it. It's okay, it's basically true, okay, fundamentally true, so to say. And these are my axioms, right? That it consists, set B should consist of at least two elements. Is it okay? Closure property should be valid. My commutation law should be valid. My associative law should be valid. My distributive law, but this should be valid. Okay, all right. And when I come to an interpretation of it, we see that the operators are such that it's valid. Okay. Then there should be some identity elements over here, and there should be complement over here. These are my basic axioms. Okay, right. On these axioms now, we will prove certain more theorems. Those will be also necessary for it. The theorems will act as rules, okay, so far as manipulating switching expressions, functions, etc. These are the theorems that I will now be describing, right? So, for example, my first theorem is that closure of identity elements. Okay. Now, Closure of identity elements, I mean this. For example, if you take a plus 1, this is equal to 1, a dot 0, this is equal to 0. That means if we take these operations, this should be 1 and this should be 0. Now, this is a theorem we say because we should be able to prove this from my fundamental axioms. Right? Let's see, just give a proof of it. Say a plus 1, right? That I want to prove that this is equal to 1, right? Therefore, let me do it. These operations I do, and you have, this is, you see, that by a6. Is it okay? That means a plus 1, this is equal to, I can write this. Okay. Now, if I write this, then I can write this also, a plus a dash, and this is by a7. Okay. Now, this is equivalent to writing a plus 1 a dash. Is it okay? This is dot I have missing. All right. This sometimes while writing we will not be given a dot. Writing side by side will assume that there is a dot already there. Is it okay? Right. Now a plus 1 a dash. This is by a6. What is a6? A6 you. Oh no, this is not by a6. 1 plus a dash. This is by a5 by law of distribution. Is it okay? Now this turns out to be 1 a plus 1, because 1 a dash, this is by a6, okay, and this is equal to a plus 1 is equal to 1. This is by a7. So a plus a dash by a6. Just 1 minute. Let's start once more. This is a plus 1 dot 1 is by a6. Is it okay? Right. Then a plus 1 dot a plus a dash. A plus a dash is what? By a7. A plus, I mean 1 is replaced by a plus a dash. That is by axiom 7. Right. Now a plus a dash is equal to 1. That is once more a plus this a. I mean after that we get this a plus 1 a dash. A plus 1 a dash is by distribution. That is by a5. Okay. 1 a dash, right, is equal to a 1 a dash is equal to 1. Sorry, this should be not 1. A plus a dash. Is it okay? This is by a plus a dash. This is by a6 once more. Okay. Right. 1 a dash is equal to a dash, and a plus a dash is equal to 1. That is by a7. Is it okay? Now this is.
So how do you come from a plus 1 dot a plus a dash equal to a plus 1 a dash?
Come once more.
A plus 1 dot a plus a dash is equal
1 is equal to a plus a dash.
Okay.
That is by a7.
From this to the next step.
This is by law of distribution. Say for example, this is a plus 1 dot. Essentially is 1 dot a dash. This is by the law of distribution. Let's count the law of the distribution. You see that a plus b dot a plus c is equal to a plus b dot c. The other way around we have taken. Is it okay? Therefore, this is essentially a plus 1 dot a dash, and 1 dot a dash is essentially a dash by a6, right? And this is therefore equal to a plus a dash equal to 1 by a7 once more. Now it's all right. Okay. Therefore, you see that this is a theorem which we have proved, okay, from the fundamental axioms. Is it okay? From the axioms. Now let's see the dual of it. Okay. Dual of it turns out to be that we'll have to prove that a dot 0, right, is equal to 0. For that we take a dot 0 plus 0. This is by a6 once more, right? A dot 0 plus a dot a dash. This is by a7. Okay. This is a 0 plus a dash. Okay. This is by a5. Right. This essentially means 0 plus a dash is equal to a dash. This is by a6, and this is a dash equal to 0. This is by a7 once more. Okay. Now come to this and this. Keeping side by side, let us see. I'm not sure whether the entire thing is coming. No, the entire thing is not coming. One thing is that, so for example, if we come to this, you see that a plus 1 equal to 1, a dot 0 equal to 0. Okay. Both of the rules are proved in the similar way, right? Only thing is this, that whenever there is a plus, okay, that is replaced by a dot for the other proof, okay, or the other statement, other expression. And whenever there is a 1, that is replaced by 0, right? This is called, in fact, a duality, okay, that any expression that is true, right, in Boolean algebra, its dual expressions is also true in the Boolean algebra. That means, how do I get a dual? I get a dual by replacing plus by dot and replacing 1 by 0. You come to all the fundamental postulates, right? So, for example, that everywhere you can see that for the commutation laws, right, that a plus b equal to b plus 1, its dual is that plus is replaced by dot, a dot b is equal to b dot a. Okay. Similarly, that for example, that complementation, a plus a dot equal to 1, plus is replaced by dot here, and 1 is replaced by 0, a dot a dash equal to 0. Therefore, you'll find that as I go to prove the other theorems also, right, depending upon this, the fundamental postulates, right, everywhere the duality holds good, right? Any expression that is true in a Boolean algebra, its dual expression is also true in that algebra, right? By that dual expressions, I mean that dot is replaced by plus, or plus is replaced by dot, okay, and 1 is replaced by 0, and 0 is replaced by 1. That is the dual expressions that I get. Okay. Now, let's come to the other theorems. Say, theorem 2. We call this an equality theorem, right? That we say that for all A, B, C contained in B, if A plus B is equal to A plus C and AB is equal to AC, then B is equal to C. That means if this is true, then this is true. Is it okay? This is called an equality theorem, right? I am not, whatever is shown in that monitor is visible from the last row? Yes. Okay. Now, this is my theorem 2. What I suggest is this, not all the theorems proofs I am showing over here. You should be able to prove all the theorems, okay, from the fundamental postulates that we have given, right? okay, and you try at your leisure, right? If you have any problem, then we'll be talking about it, right? We'll be showing about it. Now let's see, let's come to the theorem 3. It's called the complementarity, okay, this is R, okay, complementarity theorem. This says that for all A, B contained in B, if A plus B is equal to 1 and AB is equal to 0, then A is equal to B dashed and B is equal to A dashed. Right? This is complementarity theorem. It says that once more that if AB is contained in B and you have that A plus B equal to 1 and AB equal to 0, then A equal to B dashed and B equal to A dashed. Is it okay? Right. Now let's come to theorem 4. It says that identity elements are complements of each other, okay, which essentially means that 1 dashed should be equal to 0 and 0 dashed is equal to 1, right? I mean, it's not much of a problem to prove this, I think. For example, say by A6 what we have? By A6 we have that 1 plus 0 is equal to 1 and 1 dot 0 is equal to 0. Is it not? This by A6 we have, right? And if this is so, then by just the previous theorem, that means by theorem 3, that if A plus B equal to 1 and A B equal to 0, then A equal to B dashed and B equal to A dashed, that we have already a theorem exists, right? From there I can immediately say that 0 dashed is equal to 1 and 1 dashed is equal to 0. Okay? Therefore you can see that a particular theorem can be either proved directly from that axioms or from the axioms as well as the theorems that we have already proved. Okay? Therefore I suggest that you try to prove all these theorems on your own, okay, and that will give you a, I should say that a confidence also, right, regarding handling of the expressions by means of the Boolean algebra. Okay, let's come to theorem 5, right? I mean identity elements 1 and 0, okay, are unique. Okay, that's my theorem 5. Then theorem 6 is, says the complement of an element is unique, right? Now this can be very easily proved. You can see that we can go the proof this way, that if not, I mean, let's suppose this way, that if not they are unique, let A1 and A2, okay, the complements of A, the two complements exist, A1 and A2 are complements of A, right? In that case, naturally, we have that immediately A plus A1 is equal to 1 and A1 is equal to 0, okay? And in that case, we will have A plus A2 is equal to 1 and A2 is equal to 0, right? Which essentially proves that A plus A1 is equal to A plus A2, right? And A1 is equal to A2. This immediately, by equality theorem, what do I get? That A1 is equal to A2, that is by equality theorem we get, okay, which means that the complements are unique, right? Therefore, this is all right. Therefore, this is my theorem 6, okay. Let's come to the some more theorems, okay, before actually I proceed to the next step, right? These are all the theorems that we'll be needing. Theorem 7, it says that law of involution holds good in Boolean algebra. By that I mean that for all A contained in B, right, A dash is equal to A, okay. This is my law of involution. As you know that law of involution holds good in Boolean algebra. That means for all A contained in B, A dash, that means if I apply the unary operator dash twice, then we get back A, okay, right? And let's come to the next theorem, which we shall be very often will be employing, right? This is called theory of, law of idempotence, law of says that law of idempotence holds good in Boolean algebra. That means for all A contained in B, right, A plus A is equal to A dot A is equal to A, right? This holds, okay. Once more you see that everywhere it's a dual statement. If you make a statement, the dual statement we make already, and if this statement is true, the dual statement is true. Is it okay? Now let's try to give a proof of it. Very simple once more, right? Say A plus A, okay. This is, I can write it that A dot 1 plus A dot 1. Is it okay? Therefore, I can write it as say A dot 1 plus 1. This is by what law? By distribution. This is the law of distributions. This is equal to A dot 1, right? Okay. And this is equal to therefore A. Now, correspondingly, A dot A I can write as a plus 0, a plus 0 is okay. This I can write as a plus 0 once more by distribution, law of distribution, and this is equal to a. All right. Therefore, you can see that the law of idempotence, a plus equal to a, and its dual, that a dot a equal to a, are true. That I can prove, okay, from the directly from the axioms, okay. Now, let's come to theorem 9. It's called that law of absorption holds good, okay. Right. Now, what's the law of absorption? The law of absorption is, say for example, a plus ab is equal to a, right? And is a dot a plus b is equal to a. That's called the law of absorption, right? Now, let's try to prove this, okay? Let's see whether we can prove it or yes?
So the idempotence was, you took 1 plus 1 equal to 1.
Yeah.
So, but that is basically the idempotence law, that 1 plus 1 is equal to 1. That is a plus a equal to a.
Right.
So how
but at the same time, that this I get from, for example, the law of identity. Because I say that 1 and 0 are the elements of, okay, right, that come over here.
Theorem 1.
Theorem 1.
Hmm?
Theorem
A plus 1
A plus 1 equals to A.
You see that we have already proved that a plus 1 equal to 1, okay, and here that a is an element. For example, that a is for all a that is contained in B. My identity elements 1 and 0 are contained in B, therefore 1 plus 1 equal to 1, right? And similarly, therefore, anything that you put over to here, 1 or 0, that should be equal to 1 as such, okay? Let's come back to then theorem 9. A plus ab equal to a dot ab equal to a dot a plus b equal to a. Let's prove it once more, right? That a plus ab, I can say that a b plus b dash plus ab, because b plus b dash equal to 1, okay, right? This is equal to ab plus ab dash plus ab, okay, right? This is essentially ab plus ab dash, a plus a equal to a, right? Then a b plus b dash, this is a 1, this is a, right? Therefore, this is a law of absorption that is proved, okay? Let's prove the dual of it, right? Say a dot a plus b, this I can immediately write to be, okay, a plus ab, okay, right, a plus ab, and this I can write from the this, I mean the thing that I have proved already in theorem 9, that is a plus ab equal to a, right? We can write it to be equal to a, right? Therefore, we have the law of absorption, okay, proved, right? And now there is one more theorem, right? Let me talk about that theorem that is called the De Morgan's law next.